In this video, I want to take a look at exam revision for hypothesis testing. So for this video here today, all we're going to do is take a look at two exam style questions for hypothesis testing. And as you can see here, this will cover the following topics. So we have hypothesis testing for the mean of a Poisson distribution, as well as finding critical regions for a Poisson distribution. And we also have hypothesis testing for the parameter P of a geometric distribution, as well as finding critical regions for a geometric distribution. So what I'd recommend here is that you pause the video, have a go at the questions as they appear, and double check that your solution matches what we get on the screen. So that gives us everything that we need here then for this introduction. Let's take a look now at question 1. Let's get started then with question 1 here. So for question 1, we're told that breakdowns occur on a manufacturing machine at a rate of 2 per week. The manager changes a component on the machine and believes that the rate of breakdowns will change. The machine is monitored, and over a 4-week period, the manager finds that there are 2 breakdowns. So for this question here, we just want to test at the 10% level of significance whether the manager's belief is correct. So we're hypothesis testing here, so the first thing that we should do is define our hypotheses. Okay. Now to do that correctly, we need to understand what distribution we are working with here. And in this case, we're working with a Poisson distribution. And how do I know that? Well, we're talking about a rate here. So as we can see then, breakdowns occur on a manufacturing machine at a rate. So at a rate here of 2 per week. And the fact that it says 2 per week. So when we're looking at something over a time period, such as per week, per day, per month, something like that, we know we're going to be working with a Poisson distribution. Okay. So we have H0 and H1 here. So I've got H0. And obviously, if we're testing for a Poisson distribution here, we're testing for the mean of a Poisson distribution. So our parameter then would be lambda. So lambda here is equal to some value. And then we also have H1. Okay, and again, we're testing for the parameter here, lambda. Now to start with then, let's choose what this value here is for H0. Now we do need to be careful. So just read the question carefully here, because at first glance, you might think that the value here for lambda is simply 2, because it says at a rate of 2 per week. But we do need to be careful because the evidence here, so the machine is monitored, and over a 4-week period, the manager finds that there are 2 breakdowns. So because the actual time period here for the evidence is a 4-week period, as we can see here, we need to scale the original mean up here. Okay. So because this is at a rate of 2 per week, and we're looking at a 4-week period, we need to scale this up then to 4 weeks. So if this is per week, we want a 4-week period. We times this value here of 2 by 4. So 2 times by 4 would simply give me 8 there. So lambda is equal to 8. So that's the null hypothesis there, nice and straightforward. Now for H1, again, we need to be careful here. So this depends on whether we have a one-tailed hypothesis test or a two-tailed hypothesis test. So for this example here, hopefully you can see that we have a two-tailed example, okay? Because the manager's belief here is that the rate of breakdowns will change. So it doesn't imply that it's greater, so the rate of breakdowns will increase. It doesn't imply that the rate of breakdowns will decrease, just that there is some change, okay? So it's either going to increase or it's going to decrease, okay? So in that case then, we have a two-tailed hypothesis test. So in that case then, we're saying that lambda is not equal to this value here of 8, okay? So that gives us our null and alternative hypothesis there to get us started. Now, the next thing that we're going to do here is assume that H0 is true, okay? So I assume here that H0 is true. So assume H0 is true. And why do we do this here? Well, we're going to choose a random variable to model the situation here, okay? So if I choose X then as my random variable here, X will follow a Poisson distribution with parameter here of 8, okay, because we assume that H0 is true. So if H0 is true, then our parameter then is simply 8, okay? So the parameter is 8. Now, because we have a two-tailed hypothesis test here, and we're originally testing at the 10% level of significance, we need to half this to account for each tail, okay? So we half this here. So it's going to be 5% in each tail. So let's make a note of that here as well, just so we're aware of that fact. So 5% in each tail then, okay? So what are we actually testing for here? Well, that's based on the evidence. So the machine is monitored and over a 4-week period, the manager finds that there are 2 breakdowns. So what we're looking for here then is the probability. So we're looking for the probability here that our random variable x is either going to be greater than or equal or less than or equal to the evidence, which in this case is 2 breakdowns. Okay, so I'll put 2 there. Now, how do we decide the direction then of the inequality? What we do here is we look at the observed value. So our observed value here is the 2 breakdowns, and we compare that to the mean of our random variable, which in this case is 8. So because the observed value 2 is less than the mean, in that case then we're testing for our random variable x here being less than or equal to our observed value here of 2. Okay. And to find this probability here, we're going to simply use our calculator. So we go into stats mode. So if I do this as well, stats mode, distribution, Poisson, and PCD here, we have a cumulative probability. So the data type is clearly a variable. So I'll note this over here. So data type, that is a variable. For x then, so x here, that would be this value of 2. So we put x is 2 there. And then for mu here, that is the mean, which as we've mentioned is simply the parameter here of 8. So input those into your calculator, press enter, and what we get then is a probability. So I give this here to say 3 significant figures then, what do we get? Well, I get 0.0, so 0.0138. Okay, like so. And what we do now is we compare this to the significance level here. Okay, now we don't compare this to the 10%, we compare it to the 5% here for each tail. Okay, now this value here, this probability, so 0.0138, this is less than the significance level of 5%, so this is less than 0.05. So therefore, in that case, then we now reject H0. Okay. So therefore, we reject H0. So reject H0 then, and we say we have sufficient evidence at the 10% significance level to suggest that the manager's belief is correct. So let me just write all of that down. So sufficient evidence. Sufficient evidence. This is always the worst bit of any hypothesis testing question right now in the conclusion. So sufficient evidence at the 10% significance level. Make sure as well for the conclusion, you give it to the original significance level of 10% rather than what's in each tail. So it's 10% here. So the 10% significance level. To suggest that the manager's belief is correct. Okay. And there we have it. So it is important that you do give the conclusion here something like this. Don't forget that we do need to include it as well. Okay. But there we have it. So that gives the solution there to question 1. So if we take a look then at one more question here, we have question 2, where it is known that 10% of the components produced by a machine are defective. The company decides to test the components one at a time until they encounter the first defective component. The machine then receives a reset, and it is hoped that this will reduce the proportion of defective components. So to start with then for part A, as it says here, using a 5% level of significance, find the critical region for a hypothesis test that the proportion of defective components has reduced. So to start with then, let's just define our hypotheses here. So we've got H0 and H1. So we've got H0 and H1. Now clearly, to define these hypotheses correctly, we obviously need to understand what distribution we are working with for this question. And for this question here, we are working with a geometric distribution. Okay, so how do we know that? Well, simply put, the company here is looking for the first success, and they just keep going until they arrive at the first success. So in that case, then we have a geometric distribution. Okay, so we're testing for the parameter p then for h0 and for h1. Okay, so we obviously need to decide what the value of p here is equal to. So p is equal to some value, some probability here, which in this case is simply the 10%. Okay, so we're going to put that p is equal to 0.1. Now for h1, we need to decide whether this is a one-tailed hypothesis test or a two-tailed hypothesis test. Now, given that we're looking for the proportion of defective components reduced in here, as we can see, reduce the proportion of defective components, in that case then, we're testing for p being less than 0.1. So in other words, we have a one-tailed hypothesis test. Now, the next thing that we're going to do here is assume that h0 is true. So we assume that h0 is true. So assume h0 is true. And why do we do this? Well, because now we're going to define a random variable to model this situation. So we choose x here as our random variable, then x will follow a geometric distribution with parameter then of 0.1, because we assume that h0 is true. So if h0 is true, then p is equal to 0.1. Okay, so our parameter here is 0.1, like so. Now, what we need here for the critical region then is we require the probability that our random variable x here is greater than or equal to some value, let's call this c, and this must be strictly less than the significance level, which in this case is 5%. Okay, so this must be less than 0.05. Now you might think I've made a mistake here because I have the probability that x is greater than or equal to c, whereas for h1, our parameter p must be less than 0.1. But remember, for a geometric distribution, we do the opposite. So this is correct. Okay. So to find this probability here, this would simply be 1 minus p to the power of c minus 1. Okay. We do 1 minus p, which in this case then will be 1 minus 0.1 because p is equal to 0.1. And as we said then, that is to the power of c minus 1. And this must be strictly less than 0.05. Like so. Okay. What I'm going to do now is take logs here of both sides. And when I do that, I'm also going to use the power rule here to bring the c minus 1 down in front. Okay. Now clearly 1 minus 0.1 would give us 0.9. So what I get then is bracket here of c minus 1. Then we have log of 0.9. And this is strictly less than log of 0.05. Okay. What I'm going to do now here is divide both sides by log of 0.9. However, do be careful when you do this because log of 0.9 is negative. So what we're doing now is dividing by a negative number. And remember, when we have inequalities here, like we have for this line of working, when we divide by a negative number, that will flip the direction of the inequality. Okay. So what we have then is c minus 1 is strictly greater than log of 0.05 over log of 0.9. Okay, so log of 0.05 over log of 0.9. Okay, so in that case then, c must be strictly greater than 1 plus this fraction here. So 1 plus log of 0.05 over log of 0.9. Okay. Now what we need to do here is put this into our calculator then. So if you do this correctly, you will find that c must be strictly greater than 29.433, so on and so on. So we had 29.433, so on and so on. Okay. Now clearly then for the critical region here, we must round this value up to the next integer. Okay, so in that case then, so therefore the critical region here, in this case is x greater than or equal to 30. Okay, rounding up to the next integer then gives us 30. Okay, and there we have it. So that's the solution to part A. Now for part B then, nice and straightforward here. It just asks us to find the actual significance level of this test then. So in this case then, for the actual significance level, let me just write this down. So for the actual significance level, nice and straightforward here, this would simply be the probability that x is greater than or equal to 30. In other words, the probability of being within the critical region. Okay. So this is equal then to the probability that our random variable x is greater than or equal to 30. Like so. So to evaluate this here, this would be 1 minus p to the power of 30 minus 1. So we get 1 minus 0.1 to the power then of 30 minus 1. Okay, which if we simplify here, this gives us 0.9 to the power of 29. Okay, so clearly to evaluate this, you need to use your calculator. And if you do this correctly, then what you should find here is you get 0.0471. You get 0.0471. Okay, so that gives the solution to part B. And then we arrive at the very last part here, part C. So before we get to part C, then it says the company finds that the first defect is on the 25th component. Okay, so the company finds the first defect on the 25th component. So for part C, then it says comment on this in light of your critical region. So for part C then, what we're told here is the observed value is x equals 25. Okay, so x is equal to 25. Now, with this observed value here, we need to compare this to the critical region. So in other words, does this lie within the critical region or does it lie outside of the critical region? Now, clearly in this case, if the critical region is x is greater than or equal to 30, and we've observed that x is equal to 25, then clearly this falls outside of the critical region. Okay, so what we say then is as x equals 25 is not in the critical region. So this is not in the critical region. In that case, then we accept H0. We accept H0. Okay, we accept H0. Or you could also say there is insufficient evidence to reject H0. Either's fine, but I'll just make it nice and simple and just say that we accept H0 there. Okay, but there we have it. So that gives the solution to the very last part then, part C. And that gives the solution to the very last question within this video, question 2. And that actually brings us to the end of this video on exam revision for hypothesis testing.